You know all those perfect, elegant curves you see in math and in nature? I'm talking about parabolas, ellipses, hyperbolas. Ever wonder where they actually come from? Well, they aren't just random shapes. They're all born from really simple, almost secret rules. Today, we're going to uncover those rules and build their famous equations right from the ground up.
Just look at this. This is the Cathedral of Brasilia, an absolutely incredible piece of architecture, right? Well, that shape is no accident. It's a hyperbola, and it's governed by a very precise mathematical rule. Believe it or not, in the next few minutes, we're going to derive the exact equation that defines this masterpiece, starting with absolutely nothing. So, how can a simple little instruction generate such complex and beautiful shapes? Well, the answer lies in this really powerful idea called a locus of points. Now, locus sounds fancy, but it's just a way of describing a shape by the rule that all of its points have to follow. Think about a circle for a second. It's just the collection, the locus, of all the points that are the exact same distance from a single center point. The rule creates the shape. Today, we're going to check out the rules for some even more interesting shapes. And it really all boils down to these two fundamental rules. This is like the secret DNA for all the conic sections. The parabola, it's all about one point, called a focus, and one line, the directrix. But the ellipse and the hyperbola, they're both defined by two fixed points, which we call foci. That's it. These two simple ideas are all we're going to need. All right, let's see how this actually works. We're going to start with the simplest case, the parabola. Think of this as our warm-up for turning a geometric rule into a clean, standard algebraic equation. Okay, here's the setup. You can see it right here in the diagram. The rule for any parabola is that if you take any point P on that curve, its distance to the focus point F is always exactly equal to its shortest distance to that directrix line M. It's a perfect balance. And this property, by the way, is exactly why parabolas are so useful in things like satellite dishes and car headlights. They focus all the signals or light to a single point. So, in the language of math, the rule is just this. The length of PF is equal to the length of PM. Super simple, clean, elegant. Our mission, should we choose to accept it, is to turn this geometric fact into an equation with x's and y's. All right, let's start translating. We're going to use the good old distance formula. You know, the one that comes from the Pythagorean theorem to figure out the length of PF. That gives us the big square root on the left. Now, the distance from our point P to that vertical directrix line M, that's actually way easier. It's just the absolute value of x plus a. So we set them equal, and there we have it. The rule is now an equation. Now, to do any real algebra, we've got to get rid of that pesky square root. And the key move is simple but super powerful. We just square both sides of the equation. This kills the square root on the left and also gets rid of the absolute value on the right, which lets us really start cleaning things up. And here's the magic. Once we expand out those squared parts, you'll see that the x squared and a squared terms on both sides just cancel each other out. We rearrange what's left, and we end up with this beautiful, iconic equation, y squared equals 4ax. We just built this standard equation for a parabola from a single, simple rule. How cool is that? Fantastic. So now that we've got the method down, it's time for the main event. We're going to tackle both the ellipse and the hyperbola. And the really amazing part is that we can actually derive both of their equations at the exact same time from one single starting point. So here it is, the two-focus rule. For an ellipse, if you pick any point on the curve, the sum of its distances to the two foci is always some constant number, which we'll call 2a. For a hyperbola, it's the absolute difference of those two distances that's constant. So check this out. We can roll both of those definitions into one powerful starting equation. Distance 1 plus or minus distance 2 equals 2a. The plus is going to give us the ellipse, and the minus will give us the hyperbola. We'll sort all that out at the very end. For now, we just have to trust the algebra. Now, our starting equation is going to have two square roots in it, one for each distance formula. So that's the big challenge. Here's our game plan. We isolate one of the square roots on one side of the equation, square everything to get rid of it, and then simplify what's left to isolate the other square root. Okay, so after we move one of those square roots over, square both sides, and expand everything, a whole bunch of stuff, the x squareds, y squareds, c squareds, they all just drop out. It's a lot of algebra, I know, but it simplifies down beautifully to this. It's much cleaner, but notice, we've still got one more square root to deal with. So here we are, We've simplified a ton, but we're not quite at the finish line. There's still one square root hanging around. So, what do we do? How do we finish this thing off?
We do the exact same thing again. The key is to just apply the same trick a second time. We square both sides one more time. This is like the final knockout punch that gets rid of that last square root and lets us finally solve this puzzle.
Now, this is where the heavy lifting happens. We expand both sides out, then we very carefully gather all the x squared terms, all the y squared terms, and move the constants over to the other side. After all the algebraic dust settles, we get this one unified equation. I know, it looks complicated, but the secret to everything is hiding right there in that little term, a squared minus c squared.
This is where it all comes together. That a squared minus c squared expression, it shows up on both sides of the equation. To make things way, way simpler, let's just do a substitution. What if we give that whole thing a new, much simpler name? Like, say, b squared. And with that one simple substitution, our single, complicated formula just elegantly splits into two separate, beautiful equations, revealing the standard forms that we all know and love. And it all comes down to whether a is bigger than c. Remember in the ellipse case, a is greater than c, so a squared minus c squared is a positive number. We call it b squared, and our equation simplifies to the standard form for an ellipse, with that plus sign. But for the hyperbola, c is greater than a, which means a squared minus c squared is negative. So to keep b squared positive, we just define it as c squared minus a squared instead. And that one little flip cleverly changes the sign in our equation, giving us the standard form for a hyperbola, with a minus sign. And you can see the result right here. That simple little plus sign creates a closed, bounded oval, that's the ellipse. But the minus sign, it breaks the curve wide open, sending it flying off to infinity in two separate branches, the hyperbola. It's amazing that a single plus or minus sign can make such a huge difference. So why does any of this matter? Well, because these abstract equations are the literal blueprints for things all around us, from the paths of planets and comets to some of the world's most breathtaking architectural designs. Just like that cathedral we started with, the McDonald Planetarium in St. Louis gets its iconic, sweeping shape from the hyperbola. That beautiful curve you see is a physical representation of the very equation we just derived. It is literally math made solid. So think about it. We started with nothing but a simple geometric rule, and we ended up with the equations that describe everything from orbiting planets to stunning masterpieces of architecture. It really makes you wonder, doesn't it? What other hidden mathematical rules are out there shaping the world all around us, just waiting for us to find them?